For our formal lab, we will be analyzing terminal velocity. We will be determining the effect that mass has on terminal velocity. For background information, there's potential and kinetic energy, drag force, gravitational force, and terminal velocity. Potential energy is the stored energy an object has because of its position or height, and kinetic energy is the energy an object has because it is moving. Drag force is a force that opposes the motion of a falling object, is opposite to the force of gravity. Gravitational force is the attractive force between two objects with mass, and terminal force is the constant maximum speed a falling object reaches when the upward drag force balances the downward gravitational force.
The purpose of our experiment is to investigate the relationship mass has with terminal velocity by utilizing multiple masses, gravitational force, and drag force. Our research question was, how does the mass of an object affect its terminal velocity as it's falling through the air? Our experimental goal was to measure and compare the terminal velocities of different masses by using one singular plate, two plates combined, and three plates combined, all dropped from a certain height, to determine the relationship between mass and terminal velocity. We hypothesized that the plates with a higher mass will have a higher terminal velocity, because at terminal velocity, gravitational force is equal to drag force. So when rearranged to solve for the terminal velocity, we get this equation, and based on this equation, terminal velocity is directly proportional to mass. So when you increase the mass, the value of terminal velocity also increases.
This is important because it allows us to better understand the relationship between mass and terminal velocity. This is also practical in the real world since it supports professionals in designing objects that move through the air, such as airplanes or hot air balloons.
We found that terminal velocity increased with mass. The lightest plate had the lowest terminal velocity because it needed less drag to balance the smaller weight. The heavier stack needed more drag, so it fell faster. Our results match our prediction. This slide covers our setup. We tested how plate mass affected the terminal velocity while keeping size and drop height consistent. We dropped the plate from 2 meters and used Tracker to measure their motion. Our main tools were plates, tape, a ruler, and the Tracker software.
The energy pie chart shows how the plate's energy shifts as it falls. Before it's dropped, it only has potential energy. As it falls and speeds up, some of that energy becomes kinetic energy, while some of it is converted into thermal energy due to the drag. Once it reaches terminal velocity, the kinetic energy stays constant, and nearly all remaining potential energy converts into internal energy. The free body diagram explains why, before terminal velocity, gravity is larger than drag, so the plate accelerates. And then at terminal velocity, drag is equal to gravity, giving a net force of 0 and a constant falling speed. Here's our data for the 3 different plates. We have our 3 different masses. We have the area of the plates, which was the same for all 3, but that is important so we can calculate the force of drag, and then the terminal velocity of the 3 different plates that are different masses.
From our position versus time graph, the single plate drop from a height of 2 meters reached a terminal velocity of negative 0.872 plus or minus 0.07 meters per second, which it achieved at 1.043 seconds. The correlation coefficient for the linear portion of the graph was 1, indicating an excellent fit. The plus or minus 0.07 uncertainty comes from precision errors in Tracker and the fast speed of the plate being dropped. Here's our graph from Tracker and the data analysis for 2 plates. Here's our graph from Tracker and the data analysis for 3 plates. Some important physics equations we used in our investigation are the formulas for drag force, aka air resistance, gravitational force, potential and kinetic energies, net force, and area of a circle. On the right, we also calculated for the drag force. For 1 plate, we got 0.0276 newtons. For 2 plates, we got 0.227 newtons. And for 3 plates, we got 0.365 newtons.
Using F net equals F gravity minus F drag, heavier plates required a higher speed to reach enough drag force to balance gravity. That's why 3 plates reached the highest terminal velocity and 1 plate the lowest. Small drag differences came from airflow changes when plates were stacked.
For sources of error that we didn't account for, that could include small tilts in the plate that affect the drag force due to the change in surface area of the plate, any airflow in the room from any open doors or nearby vents. The way the plate was released could have varied slightly between trials, which could have created small difference in the wobbling and therefore the drag. Sources of error that we did account for was we did a consistent cross-sectional area of the plate, we did consistent plate mass, and then we did a consistent drop height of 2 meters.
The single plate had the lowest terminal velocity, and the 3 plates had the highest. Heavier setups fall faster because their large weight needs more drag force to balance it. Since mass increased more than surface area, the heavier plates reach the highest terminal velocity. Our results thus match our hypothesis.